Dear students, welcome to this NPTEL online certification course on analog electronic circuits. Myself Pradeep Mandal, associated with ENEC department of IIT Kharagpur. So, today's discussion is primarily the limitation of common emitter and common source amplifier, particularly when it is when those blocks are getting cascaded. We have discussed about the main feature performance of common emitter and common source amplifier in our previous lectures. But then today what we will be discussing it is what are the limitations of these configurations are there, particularly when we cascade them. So, let us look into the flow, what we have and where we stand today. So, this is the overall flow. Present we are in the building blocks, and under the building blocks we do have the fourth module or week fourth modules, and in this fourth module we are very close to the last item, namely the limitation of common emitter common source amplifier while we are cascading the circuit. And hence we establish the need of some other circuit configurations which are referred as buffer. So, we will be discussing those things in detail. So, what are the concepts it will be covered in this today's class? It is to appreciate what are the limitations or restrictions are there for common emitter or common source amplifier configuration. We will revisit frequency response of common emitter and common source amplifier, but then the basic difference is that we will cascade to common emitter amplifier, and then we will see that what is the effect of cascading is there in the frequency response. The effects are similar for common source also, but for completeness we are keeping both the circuits. So, those effects are getting reduced or I should say almost getting eliminated by introducing a buffer, and hence again we will be revisiting the frequency response of common emitter followed by buffer and then followed by common emitter. So, by presence of this buffer in between, we will see that it helps to retain the frequency response of the original common emitter amplifier or whatever the things we are expecting. Similar thing for the common source amplifier also. Now, when we are talking about buffer, we will see that to achieve a meaningful cascading, what are the features are required out of this buffer. So, that also will be highlighting. So, that is the overall plan. Now, the frequency response of say common emitter amplifier in this case, we have discussed more detail of frequency response of individual common emitter amplifier. Let me talk about today it is we do have two maybe identical common emitter amplifier or architecturally they are identical, and to achieve say maybe higher gain or maybe for some other reason we like to cascade this C stage, first stage, and then you may call it is the second C stage together. So, how we do that? Output of the first CE amplifier will be connecting to the input of the second CE amplifier, but of course, with the use of C2 we can isolate the DC operating point of the first stage and the second stage, and of course, the capacitor C2 it is supposed to be allowing the signal going from the output of the first stage to the input of the second stage. So, in nutshell C2 it is helping us to separate the DC operating point of the first stage and the second stage DC operating point. Now, while we will be connecting this circuit, we may be expecting that suppose we do have a gain of this stage, it is say A1, and then gain of this stage it is say A2. We may be expecting that the overall gain say A equals to A1 multiplied by A2. So, that is what we are expecting. And also in case this A1, the first stage circuit, in case if it is having some certain bandwidth, and the second stage may be having similar kind of profile, maybe it is having certain bandwidth, and then if we combined, so this is the second stage, maybe second stage frequency response, and if we combine these two stages through this cascading, we may be expecting that the overall frequency response, it may be having very high gain, and then the lower cutoff frequency, it is maybe defined by whichever the lower cutoff frequency of the out of these two stages are higher, and likewise the upper cutoff frequency, it may be decided by the upper cutoff frequency of the circuit which is having lower value. So, this is what we are expecting. The A should be having higher gain, and then the lower and upper cutoff frequency may be decided by whichever is minimum or maximum out of this individual cutoff frequency. But in our surprise, once we connect the circuit, and if we make the observation from the primary input to primary output, we will see a significant amount of change of this gain, namely this gain may drop here to some other value, and also maybe the upper cutoff frequency may come down. So, out of the observation we may see two important things, that the gain low or mid frequency gain, it may be different from the product of mid frequency gain of the two individual stages, and also the upper cutoff frequency may be different. So, let us see why we see that. Here we have drawn the frequency, the low small signal model of the individual stages, and if I say that these two stages, they are connected here. So, if we connect the two stages, then the resistance here RC1, it is coming in parallel with whatever the resistance, it will be seen by the next stage. And also if I see that input capacitance coming from the second stage, if I call say C in of the second stage, which may be primarily due to the C pi of the second stage, and then Miller affected C mu. So, this C in 2, it is getting contributed by Miller affected C mu 2 and then C pi 2 together, and then this C in 2, it may be forming a pole coming from this RC 1 and maybe the input resistance here. So, let me rearrange this circuit. Just to give a brief, that in the small signal equivalent circuit, what we have, it is voltage dependent current source here, GM1 into VBE1, where the VBE1, it is VBE of transistor 1, and then we do have the bias resistance RB1, and then base to emitter we do have R pi 1, and then base to emitter we do have C pi 1, and then base to collector we do have the C mu 1. So, considering all these small signal parameters, so what we obtain here is the overall small signal model out of the first CE amplifier. Similarly, for the second stage, second CE amplifier, we do have the corresponding small signal equivalent circuit. And let us consider that one load is connected here CL after the C2 rather C3. Now, if we further simplify this to small signal equivalent circuit, we can translate into maybe simpler version. So, in the next slide we will be showing that. So, here these two small signal circuits are coming from the previous slide, and we can simplify individual circuits like this. Say we can translate this RB1 and RPi1 together in the form of input resistance Rin1, which means that Rin1 is Rb of this stage in parallel with RPi1. And then we are keeping this C pi 1 and then C mu 1, and this part we may translate into Thevenin equivalent. So, the voltage dependent current source is getting converted into voltage dependent voltage source. So, the voltage here it is AV1 multiplied by VB1. VB1 is here, and as you know that AV1 it will be GM1 multiplied by RC1 with a minus sign. Okay. So, that is the AV1 part. So, likewise for the second stage also we do have the rearranged or simplified equivalent circuit. It is having its corresponding R in, again R in it is equal to R b of this stage R b 2 and R pi 2. And likewise here we do have gain, we do have G m 2 multiplied by R c 2, and the resistance here it is basically it is R c 2, and here also this is R c 1. So, that is how you can translate this transconductance amplifier in the form of voltage amplifier, and then input resistance and output resistance you can express in terms of internal resistances. Now, after this if you see here whatever the signal we are getting here before we connect this circuit, we obtain the voltage here, it is same as whatever, almost same as whatever the internal voltage we do have. So, we can see the voltage here it is AV1 into VBE1 before we make this connection. But then the moment we make the connection, what will happen is that this R2 it is loading the previous stage. As a result, whatever the voltage now will be getting here, it will be different from this one, and the difference is coming due to the loading effect. In other words, it introduces one attenuation factor which is defined by R into and this output resistance here. So, R into divided by R O1 plus R into. Now, depending on the relative value of this R into and R O1, it may be having different value, but typically these two resistances may be having the same order of magnitude. In our previous example, we have considered that R c it was in the range of kilo ohms, maybe around say 2 to 5 kilo ohm, and this resistance also may be in the similar range, maybe in the range of say 1 kilo ohm. As a result, we can see this factor it will be 1/3. So, this factor with this value of RC1 and Rin2, this is becoming 1/3. So, the overall gain whenever we see from primary input to primary output, here to here, the gain of the first stage considering the loading effect of Rin2, it is already having 1/3 attenuation. But whatever the voltage it is we are getting here, of course, that is considered as VBE2, and the second stage it is amplifying that. So, the voltage coming at the primary output, we can say it is say V out equals to AV2 multiplied by VBE2, and then this VBE2 it is AV1 multiplied by VBE1 multiplied by the attenuation factor Rin2 divided by Rin2 plus RO1. So, what we are getting end of it, it is and of course, VBE1 it is same as say V in. So, we can say end of it what we are getting here, it is V in multiplied by AV1 multiplied by AV2 multiplied by the attenuation factor Rin2 divided by Rin2 plus R so that attenuation factor it is Rin2 divided by Rin2 plus RO1. So, this is one attenuation, it is getting experienced due to this cascading. The second effect is on the cutoff frequency. So, let us see the cutoff frequency. What we can say, let me clear here. Yeah. The cutoff frequency, particularly the upper cutoff frequency, it is having two candidates. One is the cutoff frequency coming due to this R and then CL, and second one it is of course this resistance loaded with Rin2, and then whatever the input capacitance we do have, that may be coming from C pi and C mu of the second stage. So, the this new candidate to define the upper cutoff frequency, if you write, so we can let me write the expression of that cutoff frequency. If I say that is omega upper cutoff frequency u. So, it is coming due to the resistance RO1 and Rin2 in parallel, RO1 in parallel with Rin2, and then multiplied with the input capacitance here. So, the input capacitance in the high frequency, of course, this C2 it will not be there, whatever the input capacitance, it is coming primarily from this C pi and C mu. So, that we can write, say this is C in of the second stage, and then this C in it is C pi almost C pi and almost the C mu multiplied by the 1 plus the second stage gain AV2. Okay. And since we do have very good gain of the second stage, that makes the C in, this C in it is very significant, and as a result the pole may be created or whatever the upper cutoff frequency may be created by the C into and then this effective resistance at that node, that may define the lower cut the upper cutoff frequency. Of course, if this upper cutoff frequency it is less than whatever the original upper cutoff frequency defined by RO2 and CL was there, then only it will be prominent. So, I should say that whatever the omega u we have written, this is only one candidate, and the overall we can say that omega u of overall. So, that will be of course minimum of this omega u, and whatever the original upper cutoff frequency we do have, namely 1 by RO2 and CL. Okay. So, depending on the situation, this upper cutoff frequency may be different. So, what we have said here, it is in the next slide we are going to summarize. Yes. So, in the frequency response, what we have seen in the CEC cascaded amplifier, first of all its voltage gain, overall voltage gain AV overall. So, that is equal to AV1 multiplied by AV2 multiplied by this attenuation, which is R in 2 divided by RO1 plus R in 2. So, this is one change, and the upper cutoff frequency, as I was discussing there, it is if I write in terms of the hertz, then f u. So, that is minimum of whatever the cutoff frequency we obtain, the candidate of this cutoff frequency I should say. So, that is 1 by 2 pi RO 1 in parallel with R in 2 multiplied by C pi 2 plus C mu 2 into 1 plus A V 1. So, this is Miller affected capacitance here coming to the input, and the C pi 2 as I said that it is as it is. So, this is one candidate, and then other one it is the original one 1 by 2 pi R O 2 multiplied by C L. So, out of these two, whichever is minimum we have to consider, that is the upper cutoff frequency. So, the similar kind of exercise it can be done for common source amplifier. So, let us look into the common source amplifier also. Here again, so we do have stage 1 common source amplifier, and then another common source amplifier. Architecturally we have taken they are very similar, and we are cascading it to get higher gain. So, basically connecting the output of the first stage to the input of the second stage through this DC blocking or DC decoupling capacitor C2, and here what you have drawn it is the small signal equivalent circuit out of the first C amplifier. Note that here we have done the similar kind of exercise, namely converting the transconductance amplifier in the form of voltage amplifier. So, we do have AV1, again AV1 it is its expression is minus transconductance of transistor 1 M1 multiplied by this RD1, and here this RO1 it is equal to RD1, similar to the previous circuit CE amplifier circuit, and here R in 2 it is coming from the two bias resistors in parallel. So, I should say that R in of this stage R in 1, it is R 1 1 in parallel with R 1 2. So, similarly, for the second stage we do have input resistance R in 2, which is R 2 1 in parallel with R 2 2, and its voltage gain A V 2. So, this is equal to minus G M 2 multiplied by R D 2. Okay. So, now again for this case also, the moment we make this connection, there will be attenuation. There will be attenuation because this resistance and this resistance, they are forming a potential divider kind of circuit. So, whatever VGS will be getting to the second transistor, it is not just the entire internal voltage, rather we will be having one attenuation factor. So, VGS 2, it is R in 2 divided by R in 2 plus R O 1. So, this is the attenuation part multiplied by whatever the A V 1 into VGS 1 we are having. And of course, this VGS, it is getting multiplied by A V 2 to get the output voltage here. So, the voltage coming here again, if I call this is the final output. So, that becomes the input voltage multiplied by first stage gain A V 1. In fact, input voltage it is same as VGS 1. So, this gives the voltage coming here, and then we do have the attenuation factor R in 2 divided by R in 2 plus R O 1 multiplied by A V 2. So, if I take the A V 1 here in the denominator, so that gives the gain. So, here again the original gain, it was A V and A V 2, A V 1 and A V 2 coming from the two stages, and then in addition to that we do have this attenuation factor. And similar to the CE amplifier, again here also we do have the upper cutoff frequency, it will be getting modified. So, for upper cutoff frequency, the new candidate to define the upper cutoff frequency, it is if I call say omega u, the new candidate for the upper cutoff frequency, it is coming due to the input capacitance here C in 2 and whatever the impedance we do have at this node, namely R O 1 and R in 2. So, the expression of this new upper cutoff frequency or candidate of upper cutoff frequency, it is R O 1 in parallel with R in 2 multiplied by whatever the C in 2 we do have, and then this C in 2, it is C in 2 equals to CGS of the second stage, CGS 2, and then plus CGD 2 multiplied by 1 plus A V 2, right. So, that is the new candidate, and of course, we have to consider the original upper cutoff frequency defined by CL and the output resistance of the second stage. By the way, this resistance, it is nothing but this R D 2. So, the previous, so if I consider these two candidate, one is this one, another is coming from this one, I have to consider minimum of the two. So, again to summarize what we have, it is in the next slide we will be considering the effect on the gain, as I said, AV overall. So, that is AV 1 multiplied by AV 2 multiplied by R in 2 divided by R in 2 plus R O 1. So, we do have this attenuation part, and as I said that this R O 1, it is R d of the first stage, and R in 2, this part, it is coming from the bias circuit, namely R 2 1 and R 2 2 in parallel. And the upper cutoff frequency. So, again if we write in the unit of hertz. So, F u, it is minimum of the two candidate, one it is coming from the C in 2 and the resistance there at the cascading node. So, we do have 2 pi, then R O 1 in parallel with R O, rather R in 2 multiplied by C G S 2 plus C G S C G D, sorry, C G D 2, right, multiplied by 1 plus A V 2. So, this is the new candidate, and then previous one we are having 1 by 2 pi R O 2 and then C L. Now, next thing is that how do we minimize these two effects, namely what may be a solution. So, let us see what may be the possible solution for that. If we put a buffer, say some intermediate circuit having some important feature, we will be discussing that, such that the input resistance of this stage called R in buff, if it is quite high, then whatever the attenuation it will be getting introduced by R O 1 and R in buff, if that is approximately 1, then we can say that the cascading effect here it is very small, and also at the same time if the input capacitance of this stage, buffer stage, if it is very small, that is also needed to avoid the effect on upper cutoff frequency. So, the basic requirement here it is this resistance of the buffer stage should be very high, input capacitance of the buffer stage should be as small as possible, and similar kind of thing, the loading effect, it is also possible at this node, right. So, to avoid the loading effect at this node, what you are looking for, that input resistance of the second CAS amplifier or CE amplifier, we may not be having much control, but then in case if we say that if we make this resistance as small as possible, then the attenuation factor here it will be less, and on the other hand if this resistance it is as small as possible, even if we have decent amount of CGS and CGD and the input capacitance coming from the second stage, still we can say that the effect can be almost ignorable. So, if I write the expression of the gain of the overall circuit, so A V overall, so we do have A V 1 multiplied by A V 2 multiplied by maybe the buffer circuit having some gain A buffer multiplied by the attenuation factor coming at this node, first cascade node. So, that is R in buffer divided by R in buffer plus R O 1. So, this is one factor, and then the second factor, it is coming from this node, and this factor it is R in 2 divided by R in 2 plus R O buffer. Okay. So, first of all, to get rid of these two effect of these two factor, what we can do, we may say that we are not allowed to change this original R O 1, because if I try to change this R O 1, which is coming from the R D 1, that may directly that in fact that will affect the A V 1. So, we are not allowed to change here. So, same thing, we are not allowed to change the input resistance here. Only thing is, let us see what is the thing we can do in this buffer circuit, so that we can remove these effects. So, if you see that if I want to make this part equals to 1, what you have to do, it is we have to make this part R in buff should be as high as possible compared to this one. So, if I make this part, it is as high as possible. So, we can say this input resistance should be as high as possible, then I can make this part equal to 1. On the other hand, if I see the second factor, if I want to make it approximately 1, so what I can say that this part I can make it as small as possible. Okay. So, if I do it, at least in the gain of the entire cascade circuit, we can say that we are retaining the gain of A V 1, A V 2 and A buffer. Now, this buffer circuit is, we do have a special requirement on this impedance, namely we have to make this output resistance as small as possible, input resistance should be as high as possible. So, after achieving that, we may not be able to really do get good gain, but we have to keep in mind that this A buffer should not attenuate the original signal. Namely, we should be rather happy in case if this part it is approximately 1. Okay. So, from gain point of view, that is the requirement. And then if I see the cutoff frequency point of view, if I say that this resistance, it is this resistance is a very high. So, at this node, whatever the pole defining the maybe the potential candidate to define the upper cutoff frequency, which is 1 by R O 1, and since this resistance is very high, I can ignore that part, and then C in of the buffer, it is the end. So, to make this pole to make this pole very high, so that the overall upper cutoff frequency should not get disturbed by this cascading, what you have to do, we have to make this part as small as possible. So, likewise, if I consider this node, the cutoff frequency there, it is defined by R O buffer in parallel with R in 2, and then we do have the corresponding C in of the second stage. So, here we are already saying that we do require this R O buffer should be as small as possible. So, if this is very small, so that makes this resistance very small, and then corresponding pole here it will be going to high frequency. So, if I consider these two new candidate possible new candidate of defining the upper cutoff frequency. If you push both of them beyond whatever the original cutoff frequency we do have, namely 1 by RO2 and then CL, then we should be very happy about that. So, in other words, if both of these two poles, new poles, if we push them beyond the original cutoff frequency, then we can say that it will be the cascading will not be having effect on the bandwidth of the circuit. So, in summary, the requirement of the buffer, it is the following. Okay, this similar thing we can get for C followed by buffer and C. So, I will not be repeating this part. So, you can do yourself. Now, what we are saying is that what are the necessity or necessary features of the buffer, particularly if the circuit is in voltage mode. What we just now said that output resistance of this buffer, this resistance should be as small as possible, quote and unquote low. So, on the other hand, the input resistance of this buffer should be as high as possible. So, quote and unquote high. And then input capacitance, again it should be as small as possible, so that the cutoff frequency should not get, upper cutoff frequency should not get affected. So, again here it is quote and unquote low. And then the voltage gain of this circuit, preferably it should not be very small. So, we should be rather happy if it is in the order of 1. Okay. Now, this kind of requirement, it is essentially it will be obtained by different circuit configuration, namely common collector if it is implemented by BJT. If it is implemented by MOS transistor, it will be common drain, which means that this buffer particularly for voltage mode amplifier cascading, this buffer it will be implemented by common collector or common drain stage. Now, so far we are talking about voltage mode. Similar kind of things we may experience whenever we will be dealing with current mode amplifier, namely cascading current mode amplifier. And for that buffer, of course, we will be requiring complementary kind of features. So, what kind of circuit and what kind of features are needed, let us see in the next slide. Yeah. So, this is the required buffer for current mode amplifier cascading. What we are looking for, it is that output resistance for this case, to avoid the loading effect, output resistance, particularly the resistance wise, it should be as high as possible, quote and unquote high. And then input resistance, it is the dual effect. To avoid the loading effect, the input current should be consumed by this circuit without any problem, so that we can get the signal propagating there. So, the input resistance, it should be quote and unquote low. And then of course, the current gain, we should be happy in case we are not attenuating the signal, it may be in the order of 1. And such kind of requirements are getting implemented by the third configuration. Say for BJT, it is common base, and if it is MOSFET based, then it is common gate. So, I should say that current mode buffer, it will be implemented by this common base configuration or common gate. I think yeah, so most of the things whatever we have planned, we have covered. So, what we have we are going to conclude now, it is that The common emitter amplifier, we have seen it is having some limitation, particularly whenever we are cascading, and it's not only its gain, but its not only its gain, its the bandwidth is also getting affected. So, that can be avoided or minimized by adding appropriate buffer if you put in between wherever we are doing the cascading, and that improves or rather brings back the bandwidth and the expected high gain of the cascaded amplifier. You also have talked about the necessary features of the buffer, particularly for voltage mode buffer. Input resistance should be as high as possible, input capacitance should be as small as possible, and output resistance should be as small as possible, and the complementary things are required for current mode amplifier. In case if you have say transconductance or transimpedance amplifier, you yourself can now find what kind of features are necessary for the corresponding buffer. And so, this buffer, as I said, that it invites new kind of configuration. It is either you can say that common collector or common drain stage for voltage mode buffer, or common base or common gate for current mode buffer. So, I think in the next class we will be able to discuss more detail about those different kinds of configuration, and we will discuss about how they can be designed. That is all. Thank you for listening.